Welcome. Tonight, our journey takes us to a place more alien than the surface of the moon, a place that exists right now on our own planet, yet remains almost completely unknown. We are traveling down to the deepest point of our world, the Mariana Trench. This is not just a journey into darkness, it's a journey into secrets. We will explore the unidentified metallic sounds that echo from its walls, the phantom fish seen by the first explorers, and the strange biological paradoxes, creatures of glass and transparent hunters that would simply melt if brought to our world. And we will ask the quiet, unsettling question: how did our own ghost, a simple plastic bag, manage to reach this untouchable place before we did? If you find this slow, quiet exploration of mystery something you genuinely enjoy, I'd be grateful if you'd like the video and subscribe. Letting me know in the comments where you're listening from and what time it is for you is always a quiet comfort. Now, find your comfortable position. Dim the lights. Take a slow breath. We are leaving the map behind. That map is an illusion. We think of our world as a solved puzzle. In our minds, the globe is complete. We have satellites that can chart every street, every river, every remote mountain peak. We've photographed the entire surface, and we tell ourselves that there are no more blank spaces. But that is the great lie of the surface. Our true maps stop at the water's edge, and when they do try to show what's beneath, they are mostly guesswork, artistic renderings, vague, low-resolution sonar scans that paint the ocean floor in broad, blurry strokes. The Mariana Trench is the ultimate proof of this. It's a 2,500-kilometer-long scar on the planet's surface that has stubbornly resisted our attempts to truly see it. The reason for this ignorance is simple, and it is absolute: pressure. At the surface, we live under a gentle, comfortable blanket of air. We forget its weight, but travel down into the ocean, and that pressure builds with a crushing, relentless logic. Every 10 meters you descend, another entire atmosphere of weight is added to you. Now imagine descending 7 miles, 11,000 meters. At the bottom of the trench, the weight of the water above is over 1,100 times greater than at the surface. This pressure is an inverted force. It warps solid steel as if it were paper. It pulverizes bone. It compresses matter so intensely that it changes the very laws of chemistry and biology. This is why the moon was easier. The moon was a vacuum, a void we had to fill with our own technology, our own life support. The trench is the opposite. It is not empty space. It is an overwhelming presence, a force that pushes back with the weight of an entire world. And this is what makes the map blank. Not because the trench is empty, but because it is so incredibly full of this power, a power we were never built to withstand. It is a place that holds its secrets well. When we imagine that depth, that crushing, total darkness, we usually imagine one other thing: silence. A perfect, absolute quiet. The kind of stillness that must exist where no light or warmth can survive. We picture an empty void. But that assumption, like the map, is wrong. One of the most surprising discoveries about the Mariana Trench is that it is not silent. In reality, it can be one of the noisiest places on Earth. In recent years, scientists have lowered highly sensitive, titanium-encased microphones, called hydrophones, into the abyss. They were expecting to record a baseline of quiet. Instead, their instruments were flooded with sound. The reason for this is physics. The unique combination of pressure, temperature, and depth creates what oceanographers call a deep sound channel. This channel acts as a massive natural amplifier. Sound that enters it cannot easily escape, and it travels horizontally for thousands of kilometers, losing almost no energy. And what did these hydrophones hear? They heard the Earth's own movements. the constant, low-frequency groan of the tectonic plates grinding against each other, the very sound of the trench being formed. They recorded the deep rumbles of underwater earthquakes from half a world away. They also heard the ghosts of the surface, the distant churning thrum of a supertanker's propellers passing miles above was captured as a constant, haunting hum. Even the sound of a typhoon raging on the surface, its energy penetrating all the way down. And most haunting of all, they heard life. The low, complex songs of baleen whales echoing from oceans away. A single whale's call, trapped in this channel, can travel across an entire ocean basin. The trench, it turns out, is a planetary echo chamber. It's a place that remembers and carries almost every deep sound the world makes. Those sounds, the Earth, the ships, the whales, are the ones we can identify. But the recordings that truly puzzle researchers are the anomalies, the sounds that do not fit a known pattern. For decades, the most famous of these was a sound called the Bloop. It was an ultra-low frequency, high-amplitude sound recorded in 1997. It was so powerful that it was picked up by hydrophones thousands of kilometers apart, and for a time, it was the perfect candidate for a deep-sea creature, something far larger than even a blue whale. The truth, it turns out, was almost as interesting. Scientists eventually traced the sound not to a living thing, but to the catastrophic cracking and breaking of a massive ice shelf in Antarctica. It was the sound of ice, not a monster. But the Mariana Trench has its own stranger symphony. In 2014 and 2015, researchers deploying deep-diving floats in the trench recorded something new, a sound they could not explain. It was a bizarre 5-part call lasting just over 3 seconds. It started with deep groans like a foghorn and then suddenly leapt into a high-pitched, almost metallic twang. They called it the Western Pacific Biotwang. They listened again and again. It did not match any known whale. It did not sound like any geological event. It was complex, repetitive, and seemed for all the world like a signal. To this day, the leading theory is that it might be a new, undiscovered call of a minke whale. But it's just a theory. No one has ever seen one make this sound, and its mechanical quality doesn't sound like anything a whale should make. And then there are the other reports. The unconfirmed, almost anecdotal stories from submarine crews and deep-sea researchers. The sound of clanking metal in a place where no metal should be the sound of organized tapping from the darkest part of the abyss. Are these just the echoes of old shipwrecks settling on the seabed, or the clatter of rocks in a submarine canyon? The trench, it seems, is very good at keeping its more unusual noises a secret. That is the question that haunts us. When we hear an unknown sound from a place we cannot see, our imagination rarely paints a small, simple picture. It tends to imagine something large. In the modern world, there is one specific giant we love to imagine in the deep, a shadow that has swum from prehistory into popular culture, Megalodon. The idea is a powerful one, that a 60-foot shark, an apex predator from a bygone era, could have survived. That it simply fled the cooling surface waters of the ice ages and found refuge in the one place on Earth we have not fully checked. But this seems to be one secret the trench does not keep. The science itself presents a difficult barrier. A creature like Megalodon, a massive, warm-bodied predator, would have needed a staggering amount of food, a constant supply of large prey. The deep ocean, by contrast, is often described as a food desert. Life there operates on a budget of starvation, mostly surviving on the sparse marine snow that drifts from above. A megalodon would likely starve. The evidence for its survival in the form of modern teeth or remains is non-existent. And yet, the idea of giants in the deep is not wrong. In fact, it is one of the strangest truths of the abyss. While the trench may not be hiding the giants of the past, it appears to be actively creating new ones. In the dark, in the cold, under that relentless pressure, a biological mystery occurs. It is called deep-sea gigantism. It is a phenomenon where creatures that are small and insignificant on the surface, like shrimp or lice, evolve over time into slow, lumbering, and unusually large versions of themselves. So the fantasy of a giant is correct, but we may have been looking for the wrong kind. The trench doesn't seem to support the fast, warm-bodied hunters of our imagination. Instead, it fosters a different kind of giant, slow, pale, and adapted to a world of cold and patience. But those true giants, those pale, slow creatures, were unknown to us for the longest time, because to find them, we had to do more than send microphones, we had to go ourselves. In 1960, two men did just that. Their vessel was the Trieste, a Swiss-designed, American Navy-owned bathyscaphe. It was a novel design, a massive float filled with gasoline, which is lighter than water and resists compression, with a tiny reinforced steel sphere hanging underneath. Inside that sphere, barely large enough for them to sit, were Jacques Piccard and Don Walsh. Their mission was to be the first to touch the deepest floor on Earth, the Challenger Deep. The sphere was built to withstand the pressure, its walls 5 inches thick, but no one really knew if it would hold. The calculations were theory. The trench was reality. The descent was slow, taking almost 5 hours. They fell through the last light into the total frigid darkness. And then, at over 30,000 feet, nearly 10,000 meters down, it happened. A sound that no one in human history had ever heard at such a depth. A single, sharp, and very loud crack. It was not a creak or a groan. It was a clear, structural bang that shuddered through the entire vessel. In that moment, they were the two most isolated human beings on the planet, suspended in total darkness, 7 miles from the sun, with no hope of rescue, and they had just heard what sounded like their tiny sphere failing. For a long, tense moment, they watched their instruments, checking for a leak or a change in pressure. Nothing. They eventually discovered the source. It was not the hull. It was an outer plexiglass window on the entry tube, a non-structural piece that had finally surrendered to a force it was never designed to bear. The inner sphere, the one keeping them alive, was holding. They made a decision. They did not ascend. They kept sinking, pushing on, past the point of known engineering and into the absolute unknown, until, hours later, their small craft settled gently onto a fine, pale silt. They had landed. The silence that followed that violent crack was now a different kind, the silence of arrival. Outside their tiny viewport, the cloud of fine silt stirred up by their landing began to settle. They switched on their powerful external lights, cutting the first man-made cone of white into a darkness that had existed for eons. The world they saw was simple. A flat, pale, undisturbed plain of what looked like fine, creamy mud. The floor of the world. And then, in that beam of light, something moved. Both men, Piccard and Walsh, reported it clearly. They saw a creature. It was not a sea cucumber, not a shrimp. It was, they insisted, a flatfish. Something like a sole or a flounder, about a foot long. It had eyes. It looked at their light and then, disturbed by their arrival, it swam slowly away, disappearing back into the darkness. On the surface, this report was a revolution. It was not just proof of life, it was proof of complex, vertebrate life. A fish, an animal with bones, eyes, and a nervous system, thriving under a pressure that was supposed to make such biology impossible. Or was it? In the decades since that first historic dive, that flatfish has become a ghost. It is a persistent, haunting scientific controversy. No other mission, Not James Cameron's, not any of the dozens of robotic probes that have since visited the Challenger Deep has ever seen another one. Not a single photograph, not a second of video, has ever captured a vertebrate fish at this, the absolute maximum depth. The scientific consensus today is that Pickard and Walsh were most likely mistaken. The pressure at that depth, we now believe, is simply too great. At 11,000 meters, the force is so extreme that it can inhibit the very proteins and calcium that vertebrate life depends on. A fish's cells, its very structure, would struggle to function. So what did they see? The most likely candidate, scientists argue, was a sea cucumber, an invertebrate. Some species of holothurian that live in the deep ooze can be pale, flat, and use fin-like appendages to swim in a way that mimics a fish. But the men who were there, the only two human witnesses, never backed down. They insisted they knew the difference between a fish and a sea cucumber. And so the mystery remains. Were they wrong? Was it just a pale, slow-moving invertebrate, their minds understandably shaken after a 7-mile, window-cracking descent? Or did they get a 1-second glimpse of a true vertebrate that has somehow broken the laws of biology, a phantom that has simply never been seen again? That first dive in 1960 cracked the door open, but it would be more than 50 years before another human being returned to that specific, deepest spot. This time, the vessel was completely different. It was not a clumsy balloon-like bathyscaphe. It was a sleek, futuristic, 24-foot-long green torpedo, engineered to fall, not float. It was the Deep-Sea Challenger, and inside there was not a crew of 2. There was only 1. In 2012, the film director James Cameron, a man long obsessed with the ocean, decided to complete the journey his predecessors had started, but he wanted to do it alone. His descent was, in contrast to the Trieste's, fast and modern. He fell through the darkness at a rate of 500 feet per minute. But the psychology of the journey was perhaps even more intense. Imagine the isolation. The Trieste crew had each other's presence to anchor them. Cameron had only the hum of his electronics and the sound of his own breathing. He was encased in a steel sphere so small he could not fully extend his arms, his knees tucked to his chest, for hours. As he fell, he was not just leaving the world behind, he was leaving humanity behind. He was becoming, literally, the most isolated human being on the planet. More isolated even than the astronauts on the space station, who could at least look down and see the world in their window. Cameron looked out his tiny viewport and saw only a crushing, featureless, and total black. He described the feeling not as fear, but as a profound, almost philosophical solitude. He felt, he said, a sense of presence, the deep, quiet weight of a place that was not meant for him, a place that was utterly indifferent to his survival. He was a visitor in a realm that did not and could not ever know him, a single point of warmth and light in a cold, dark, and ancient eternity. That profound alien solitude was not the only thing James Cameron found. He was there as an explorer, a filmmaker, hoping to capture an image of something new, a strange life form, a bizarre geological feature, anything that would define this deepest of frontiers. He did find something that defined the frontier, but not in the way he or anyone had hoped. As his powerful lights scanned the pale, silty floor in the most remote, most inaccessible, most untouched place on planet Earth, he saw it. It was not a phantom fish. It was not a new species of giant amoeba. It was a plastic bag. There, 7 miles down, in a place that had resisted humanity for all of time, was the casual, immortal signature of our own carelessness, a simple piece of trash. Think of the weight of that discovery. We had barely managed to send 2 and then 1 human being to this spot. It had required the absolute limits of our engineering, bravery, and wealth, and yet our garbage had gotten there first, effortlessly. It had simply sunk, drifting down through the darkness for weeks or months or years until it settled on the bottom, a synthetic ghost arriving before we did. This discovery was a quiet, unsettling realization. It proved that there are no more truly blank spaces on the map. It showed that no place, no matter how deep, how dark, or how crushingly hostile, is safe from our influence. The most alien place on Earth suddenly felt uncomfortably familiar. It showed us that our reach has exceeded our grasp. We have managed to contaminate a world we do not even understand. And it was a chilling preview of a darker secret, that this deepest of trenches, this pristine abyss, may in fact be the planet's final, darkest, and most hidden garbage dump. So how did this place come to be? This abyss that reflects our carelessness, what is it, geologically? We call it a trench, but that word is a bit misleading. It suggests a ditch that was dug or a simple crack that split open. The truth is a far slower and much more powerful process. The Mariana Trench is the direct result of a collision. It is a place where the Earth is actively, at this very moment, recycling itself. It is formed by 2 of the planet's massive tectonic plates. For millions of years, the vast, ancient Pacific plate has been crawling across the ocean floor, and for just as long, it has been crashing into the smaller, younger Philippine plate. In this colossal, slow-motion impact, the Pacific plate, being older and denser, is the one that gives way. It is forced to dive, to bend, and to scrape under the Philippine plate. This process is called subduction. But what is hard to imagine is the scale. This is not a clean or simple event. It is a grinding, tearing, and splintering of the entire crust. As the Pacific plate is forced down into the Earth's hot mantle, it drags the edge of the overlying plate down with it, creating that deep, V-shaped scar on the ocean floor. The process is impossibly slow. The plates move at about the same speed that your fingernails grow, a few centimeters a year. But over the span of geological time, that slow, relentless movement has carved a chasm deeper than Mount Everest is tall. So when we look at the trench, we are not looking at a static feature. We are looking at a live, ongoing geological event of immense power. And this grinding, constant movement is not a smooth or quiet affair. It is an engine for some of the planet's most dramatic events. That grinding, swallowing motion of one plate diving beneath another is not a smooth process. It is a messy, violent, and chaotic affair. As the Pacific plate is forced down into the mantle, it does not just slide. It scrapes, it bends, and in some places it gets stuck. For decades or even centuries, a section of the plate will lock in place, resisting the movement. But the rest of the plate, the unstoppable mass of a continent-sized slab, keeps pushing. The tension builds, an incredible amount of stress accumulating in the rock miles and miles below the seabed. It builds and builds until finally the rock can no longer hold it, ruptures. In that instant, all that stored energy is released in a single violent jolt, an earthquake. But these are not the earthquakes we are used to. They are not the shallow shudders of the surface. The Mariana Trench is a subduction zone, and it gives birth to some of the most powerful and by far the very deepest earthquakes on the planet. Most quakes happen in the top 50 kilometers of the Earth's crust. In the trench, they are recorded happening hundreds of kilometers down. This is a profound geological puzzle. At that depth, the heat and pressure are so immense that rock should not be brittle. It should bend like putty, it should not break. And yet it does. It shatters. We are recording tremors from a place we thought was geologically incapable of them. And while these deep tremors are too far down for us to feel them directly on the surface, they are often the trigger. When that tension releases, it can transfer that massive energy upward, causing the entire overlying plate to lurch. When that happens, the plate acts like a giant paddle. It displaces a column of water miles high, pushing the entire ocean, and can be the starting point for some of the most powerful tsunamis. The trench, it seems, is a quiet, hidden engine for change on a massive scale. But that violent tectonic shifting is not the only way the Earth's deep energy escapes from the trench. It also leaks. When we think of ocean vents, we usually picture fire. We imagine the black smokers seen in documentaries, superheated, toxic plumes of black smoke boiling out of the seabed. And the trench has those. But it also has something else, something stranger, a place that seems to follow a different set of rules. Near the Eifuku volcano, within the Mariana Trench system, scientists discovered a field of vents. As their robotic submarines approached, they saw chimneys venting fluid, but there was no black smoke. There was no fire. Instead, rising from the cracks in the rock were shimmering pearlescent bubbles. They were venting almost pure liquid carbon dioxide. On the Earth's surface, CO2 is a gas. To make it a liquid, you need extreme pressure and very low temperature. The trench, it turns out, provides the perfect conditions. It is the only known place on Earth where this happens naturally. The scientists who discovered it named it, appropriately, the Champagne Vent. The view is surreal. It is a slow, cold and steady stream of liquid gas bubbling up from the planet's mantle and rising like the fizz in a glass of champagne. It is a glimpse into a truly alien chemistry, a world where the rules are so different that a gas we exhale becomes a bubbling liquid flowing from the rock. This cold, strange place is a reminder that the trench is not just a physical location, but a chemical one. The pressure doesn't just crush, it creates conditions and materials that cannot exist anywhere else on the surface. But not far from this cold, strange anomaly, its fiery twin does exist, a place where the trench stops leaking and starts instead to boil. These are the more famous hydrothermal vents, known as black smokers. In these zones, the ocean floor is thin. Seawater seeps down through cracks in the Earth's crust, traveling miles deep until it gets close to the magma, the molten rock of the mantle. There, it is superheated to an almost unbelievable degree, over 400 degrees Celsius, or 750 degrees Fahrenheit. Hot enough to melt lead. But at this depth, under this much pressure, the water cannot boil. It cannot turn to steam. It simply becomes a pressurized, acidic, superheated fluid. This fluid dissolves the rock around it, becoming a thick, toxic soup, rich with minerals like sulfur, iron, and zinc. And then it finds a way out. It shoots back up into the ocean, blasting out of chimney-like structures on the seabed. The moment this 400-degree acidic fluid hits the near-freezing ambient water of the trench, the dissolved minerals instantly solidify. They precipitate, creating a cloud of fine, dark particles that looks exactly like thick, billowing black smoke. It is one of the most raw, direct scenes on the planet, a place where the superheated interior of the Earth meets the cold, crushing deep of the ocean. For decades, we assumed these places were sterile. What could possibly survive a blast of acidic water hot enough to melt lead? What could live in a darkness poisoned with sulfur? We believed that all life on Earth ultimately drew its energy from the sun. But when our robots finally reached these black smokers, they found them teeming, swarming, covered with life. They found forests of pale giant tube worms, 6 feet long, with no mouth and no stomach, feeding on chemicals. They found fields of ghostly white crabs, blind, scuttling over the chimneys. They found shrimp clustered so densely they seemed to be boiling in the shimmering water. This discovery was a shock. Here, in this toxic, superheated water, was life that did not need the sun. It did not rely on photosynthesis. It was a new biology, thriving on chemosynthesis. The creatures here were feeding on the toxic sulfur and chemicals, drawing energy from the raw heat of the Earth itself. This find suggested that life had a second, entirely different playbook. That discovery of chemosynthesis did more than just reveal a new ecosystem. It threw a shadow of doubt over our most fundamental story, the origin of life itself. For generations, the favored theory of our creation was a gentle one. We called it the primordial soup. We imagined life beginning in a warm little pond, as Charles Darwin famously wrote. A shallow pool on the Earth's surface, bathed in sunlight, struck by lightning, where simple chemicals slowly, over eons, assembled themselves into the first living cell. It was a story born of light and air. But these black smokers, these violent, superheated chemical furnaces in the dark, offered a new, far harsher, and perhaps more plausible alternative. This is the hydrothermal vent hypothesis. The theory argues that these vents are the perfect self-contained laboratories for creating life. They have all the necessary ingredients. They have water. They have extreme heat, which acts as the engine for chemical reactions, just as lightning might have on the surface. And most importantly, they have a powerful gradient. On one side, you have the superheated, acidic, mineral-rich fluid from the Earth's core. On the other, you have the cold, slightly alkaline water of the deep ocean, where these two meet, in the porous, microscopic cracks of the chimney rock, a powerful chemical energy is unleashed. It is like a natural battery. This is a place where hydrogen and methane, the building blocks of life, are abundant. It's a place where tiny iron sulfide pores in the rock could have acted as the first cells, concentrating these chemicals and allowing them to organize. It's a compelling idea. Life may not have started gently in the sun. It may have been forged in the dark, in a pressurized and seemingly harsh environment. If this theory is true, it means the trench is not just a strange biological sideshow. It could be our home, the shared, dark and chemical-rich birthplace for every living thing on Earth, and it also suggests something important about the universe. If life can begin here, in total darkness, then perhaps the sun is not a requirement for life at all. To find these strange life forms, however, you must enter a realm that is almost mythological. Scientists divide the ocean into zones of light: the sunlight zone, the twilight zone, the midnight zone. But below that, at around 6,000 meters, you enter a place so deep that it was given its own separate classification. It is called the Hadal zone. It is named appropriately after Hades, the ancient Greek god of the underworld. It is the realm where life as we know it was thought to be impossible. The Hadal zone is not just a deeper, darker version of the ocean. It is a fundamental shift in the rules of biology. The defining feature is the pressure, which at this depth stops being a simple physical force and becomes a biochemical one. The extreme pressure actively attacks the building blocks of life. It invades the membranes of cells, making them rigid and unworkable. It can contort the very shape of proteins, stopping enzymes from latching onto other molecules. It essentially halts the engine of metabolism as we know it. For a complex animal from the surface, a descent into the Hadal zone would mean death, not from being crushed, but from a system's failure. The nervous system would fail. The proteins would unwind. The cells would simply cease to function. This is why, for the longest time, we believed the Hadal zone was sterile. We believed it was a biological, forbidden zone. But life, it turns out, is more stubborn than our theories. Life did not just visit the Hadal zone, it adapted. It rebuilt itself from the ground up to see this impossible pressure not as a hostile force, but as a normal, necessary part of its existence. The creatures that live here are biochemical marvels, having solved problems we are only just beginning to understand. So what, then, is the master of this Hadal underworld? What kind of creature would you expect to be the apex predator in a realm of 1,100 atmospheres of pressure? Our imagination pictures a leviathan, something armored with a thick shell and a dense skeleton, a creature built like a tank to resist the crushing weight. The reality, discovered only a few years ago, is the complete opposite. And it is far more strange. The most successful predator in the deepest part of the Mariana Trench is a fish. It is called the Mariana snailfish, and it is a ghost. It is about the length of your hand. It has no scales. Its skin is a translucent pale pink, almost completely transparent. Allowing you to see its organs functioning inside its skeleton is not hard, calcified bone, but is made mostly of flexible cartilage. It is fragile, it is soft, it is almost gelatinous, and it is the king of the abyss. This creature is the ultimate example of Hadal biology. It does not fight the pressure, it has joined it. The snailfish's body is a marvel of adaptation. To survive, it did not build walls, it opened the gates. Its cells are filled with special molecules called piezolites, which literally hold the cell's proteins and membranes together, preventing them from being squeezed apart by the pressure. Its body is, in essence, a gel. It has achieved a perfect, delicate equilibrium with the 16,000 pounds per square inch of force pressing in on it. This is also why it is a phantom. This fish can only exist at that depth. If you were to bring a Mariana snailfish to the surface, it would not explode. It would do the opposite. It would melt. Without the immense pressure holding it together, its very structure, the cells and proteins that were built to be supported by that weight, would simply fall apart. It would dissolve into a gelatinous slurry. It is a creature that cannot leave its prison, because that prison is also its life support. It is an animal built of pressure, a soft, translucent hunter that glides through a world that would vaporize us. The snailfish is not alone in its ghostly appearance. In the Hadal zone, and in the deep midnight zone just above it, evolution seems to have arrived at the same strange conclusion over and over. If you cannot fight the environment, join it. And if you cannot hide, you simply disappear. In a world of total darkness, there are no shadows. There are no caves or forests to hide in. It is just open, pressurized water. The only way to truly hide is to not be seen. The best camouflage, it turns out, is to become invisible. And so, the deep is filled with creatures that are essentially made of glass. One of the most spectral is the telescope octopus. It is almost entirely transparent. It's a gelatinous, slow-moving creature. Its body is so clear that the only things you can really see are its digestive tract and its two enormous, stalk-like eyes. These eyes are what give it its name. They are tubular, like binoculars, and they can rotate. They point upwards, constantly scanning the darkness above for the faintest silhouettes of prey or for the shadows of predators hunting with their own lights. Then there is the glass squid. Like the octopus, its body is a perfectly clear, fragile balloon. It hangs in the water, almost undetectable. But this creates a problem. Its eyes and digestive gland are opaque. They would cast a shadow if a predator's light hit them. The squid, however, evolved an ingenious solution. It uses its own internal light, its bioluminescence, not as a beacon, but as counter-illumination. It produces just enough light to match the faint glow from above, effectively erasing its own shadow. It is a living invisibility cloak. These creatures are the phantoms of the abyss. They have engineered themselves out of existence, becoming living windows, fragile beings that float through the darkness, proving that in this extreme world, the best defense is not armor, but absence. To become invisible is one strategy in this permanent night. But there is another, more active and perhaps more counterintuitive solution. If you cannot disappear, you must control the dark. You must make your own light. This is the world of bioluminescence. In the deep ocean, light is not a gentle ambient presence. It is a tool, and because it is so rare, it is incredibly powerful. It is a language, a lure, and a weapon all in one. The most famous master of this is, of course, the anglerfish. It is a creature that seems perfectly designed for an environment of absolute scarcity. It is, in essence, a vast mouth with a built-in fishing rod. Its body is globular and dark. Its teeth are needle-sharp and curved inward, ensuring that anything captured has no chance of escape. But its true genius is its efficiency. The anglerfish cannot afford to waste energy chasing prey in this vast, empty blackness. So it does not hunt, it waits. It hangs motionless, and from its head sprouts a long, fleshy filament. At the end of that filament is a glowing, fleshy bulb called an esker. This light is not the fish's own. It is a living, symbiotic colony of bacteria, glowing faithfully in the dark. The fish provides them with a safe house and nutrients, and in return, they provide it with a constant, hypnotic lure. A smaller fish or crustacean navigating the dark sees this single pale blue light. It is the only point of interest in a featureless world. Perhaps it looks like a potential meal, a smaller microorganism. They drift closer. The anglerfish, sensing the movement, waits until the last second. With a sudden snap of its jaws, the world ends for that small creature. The hunter has captured its meal using almost zero energy. Other creatures are more aggressive. The dragonfish, for example, is a long, black, eel-like creature with fangs so large it cannot even close its mouth. It, too, uses glowing lures on its body to attract prey. But it also has a secret weapon, a piece of biological engineering that is almost unbelievable. The dragonfish has evolved a pair of searchlights just beneath its eyes. These are not blue or green, the common colors of bioluminescence. They glow with a deep, far-red light. This is a revolutionary advantage. In the deep ocean, the only light that penetrates from the surface is blue. As a result, almost every creature in the deep has evolved to see only the blue part of the spectrum. They are, for all practical purposes, completely blind to red light. The dragonfish, however, is one of the very few creatures that can both produce and see this red light. This means it has developed a biological sniper scope. It can shine its red beams forward, perfectly illuminating its prey. The prey itself, unable to perceive red, continues to swim in what it believes is total, absolute darkness. It is completely unaware that it is being watched, targeted, and hunted by a predator that has its own, private, invisible spotlight. In this world, light is a complex and deadly game. It is a lure, a threat, and a way to find a mate. And for the dragonfish, it is a private spotlight, giving it the ultimate advantage in the permanent dark. The anglerfish and the dragonfish are the sophisticated hunters of the mid-water. They play their games of light and shadow in that open, empty blackness. But on the seabed itself, on that vast, silty plain at the very bottom, life takes on a different form. It is less about the quick, energetic hunt, and more about slow, methodical processing. It is a world of sifters and grazers. When researchers first sent cameras down to the floor of the Challenger Deep, they saw them scattered everywhere in the ooze. At first, they did not look like much. They looked like small, delicate, flat sponges. Some resembled pale, lumpy, discarded brains. Others had built intricate flower-like or root-like structures. But they are not sponges. They are not plants. They are not coral. They are xenophyophores, and they represent one of the greatest paradoxes of the abyss. The reason they are a paradox is their structure. That entire complex-looking organism, sometimes as large as your fist, or even a dinner plate, is not a colony of thousands of creatures. It is a single cell. These are, by a vast margin, the largest single-celled organisms on Earth. They are, in essence, giant amoebas. They have no organs, no nervous system, no brain, no cooperation. It is just one enormous, sprawling bag of protoplasm. They are the simplest form of animal-like life, scaled up to a giant's proportions, and they have chosen the most complex and extreme environment on Earth as their home. How do they do it? They survive by slowly moving across the mud, absorbing nutrients from the silt, filtering the marine snow that has fallen all this way. But their true genius, if you can call it that, is in their architecture. To protect their single fragile cell from the environment, they build a complex, branching shell around themselves. But they do not grow this shell like a snail does. They are collectors. They are microscopic masons. They sift through the ooze, carefully selecting specific materials from the sediment, grains of sand, the tiny, beautiful shells of other dead organisms, mineral flakes, and they glue them together using a kind of biological cement they secrete. The structures they build, called tests, are astonishingly intricate. They are not solid, heavy walls, but lightweight, porous, and strong lattices. This structure gives them a massive surface area, allowing them to absorb as much of the sparse nutrients from the water as possible, while also giving them a protected shape. The trench is full of them. They are a fundamental part of the ecosystem, creating the first level of structure on the otherwise flat, barren mud. And they are a strange lesson in evolution. In a place defined by crushing pressure, a place that makes it almost impossible for complex life to build hard skeletons of calcium, the most successful and largest creatures on the very bottom are the simplest of all. They are a reminder that in the trench, the rules are not just different, they are often inverted. It is the humble amoeba, not an armored leviathan, that seems to have inherited the deepest dark. The giant amoeba is a marvel of simplicity, but it is not the only creature that has achieved an unusual size in the deep. While the xenophyophore became large by not being complex, another creature took a different path. It followed a strange, unsettling rule of the deep ocean, a phenomenon that scientists call deep-sea gigantism. This is a rule that takes the small and familiar and scales it up to an unnerving size. All over the world's oceans, in shallow water and on beaches, there is a tiny common crustacean called an amphipod. You have probably seen them. They are like sandhoppers or freshwater shrimp, small, scurrying creatures, rarely larger than a fingernail. In the grand scheme of the ocean, they are insignificant. When scientists first sent the baited traps down into the Mariana Trench, they were not sure what to expect. They were hoping for new species, perhaps the ghostly snailfish or other strange creatures. When they pulled the traps back up, they were not empty. They were filled, swarming with amphipods. But these were not the small, fingernail-sized creatures from the surface. The creatures that crawled inside the traps were pale, white, and unusually large. They were the size of a human hand. Some were measured at over 20 centimeters. One, captured in a different trench, was over 34 centimeters long, the size of an adult's shoe. This is the supergiant amphipod, Alicella gigantea. It is in every way the same humble, simple creature from the shallows, but in the trench, it has been magnified, as if a common house spider grew to the size of a dinner plate. This discovery was a biological shock. Why does this happen? The theories are still just theories, but they offer a fascinating glimpse into a different kind of life. One idea is that the extreme cold of the deep water, combined with the pressure, slows down a creature's metabolism to an almost glacial pace. These creatures don't grow faster than their surface cousins. They just live longer and perhaps never receive the biological signal to stop growing. In the warm, fast-paced surface world, life is short. In the deep, it is slow and long. Another theory ties into the scarcity of food. Gigantism might actually be an advantage in a food desert. A larger body is a better storage unit. It can hold more fat and more reserves. When a rare, large meal does arrive, like a whalefall, a giant amphipod can gorge itself, storing enough energy to survive for months or perhaps even years before the next feast. Whatever the reason, the supergiant amphipod is one of the most striking residents of the trench. It is not an alien monster from a bygone age. It is something we know. It is a common, everyday creature, twisted by the darkness, the cold, and the pressure into a pale, armored giant that swarms the deepest floor on Earth. So, this entire strange ecosystem of ghosts, giants, and glass creatures raises a fundamental question. What does it run on? We have these apex predators like the snailfish and these massive scavengers like the supergiant amphipods. But an ecosystem cannot be made of only scavengers and hunters. There must be a foundation, a primary source of energy. On the surface of the Earth, that energy is obvious. It is the sun. It fuels the plants, which feed the herbivores, which in turn feed the carnivores. It is a short, energetic, and obvious chain. In the Hadal zone, 7 miles down, there is no sun. There is no plant life. The black smokers, the hydrothermal vents, are one answer. They provide a powerful chemical energy source. But they are rare. They are tiny, localized oases of life in a desert of mud that stretches for thousands of kilometers. They cannot be the only answer. They cannot be what fuels the snailfish and the giant amoebas miles away, out on the cold, flat plains. The true fuel of the abyss is something far simpler, far quieter, and far more constant. It is a slow, endless, gentle rain of organic matter drifting down from the sunlit world, miles and miles above. Scientists call it marine snow. It is a blizzard, not of ice, but of the remnants of life and death. It is composed of the microscopic, glassy shells of dead plankton. It is fish scales. It is fecal pellets from the creatures of the mid-water. It is dust. It is the decayed, fragmented bodies of every surface creature that has died and begun its long, slow fall. This snow is the lifeline. It is the only meager connection between the bright, fast, energetic world of the sun and the cold, dark, slow world of the trench. But the journey is impossibly long. A single particle of marine snow, a fragment of a plankton shell, can take weeks and sometimes months to complete its descent from the surface to the floor of the trench. And on that long journey, it is picked apart. The creatures of the twilight zone get the first chance, then the creatures of the midnight zone. An estimated 90% or even more of this snow is consumed, recycled, and reconsumed by the inhabitants of the mid-water before it ever reaches the deep floor. What finally arrives at the bottom is the last, most nutrient-poor remnant. It is the crumbs from a feast that happened miles above and weeks ago. It is a faint, constant, and barely nutritious dusting that settles on the mud. And on this is what almost everything depends. The giant amoebas absorb it. The amphipods sift the mud for it. The sea cucumbers ingest it. This is the base of the food chain. Life in the trench is an economy built on starvation. It is a world of extreme, almost unimaginable patience, where creatures must wait for weeks for a meal that has taken months to arrive. This is why life there is so slow. It is why metabolisms are glacial. It is a world perpetually waiting for the snow to fall. a kingdom built entirely on the microscopic leftovers from a heaven it will never, ever see. For decades, we assumed this marine snow was the entire system. It was the only story that made sense. We believed that all life in the deep mud was part of this simple vertical chain. Wait for the snow, eat the snow, and be eaten in turn. But recent discoveries made by drilling deep into the ocean floor have opened the door to a far more radical and stranger idea. What if there is another ecosystem down there? A separate parallel biology that does not rely on the surface world at all. This is the theory of the shadow biosphere. When scientists drilled into the sediment, sampling the mud and rock beneath the trench floor, they found microbes. This, in itself, was not a shock. The shock was what these microbes were eating. They were not clustered at the surface of the mud, waiting for the rain of marine snow. They were buried deep, deep within the sediment, and even within the pores of the solid rock itself, and they were active. They appeared to be living on a diet of pure chemistry. Some of these microbes seem to be eating the rock itself, stripping electrons from minerals in a chemical process that is incredibly slow but steady. But an even more fascinating theory suggests they might be living on something else. We are now discovering microbes that can survive on radiation. The natural, low-level radioactive decay within the planet's rock and sediment releases a tiny, tiny amount of energy. But it is constant. It has been there for billions of years. For a microbe that has slowed its entire metabolism down to an almost timeless state, this faint radioactive pulse might be enough to live on. This is a profound speculation. If it's true, it means there are creatures on Earth that live in a completely sealed system. They are not part of our sun-based food web. They are not connected to us, to the whales, to the plankton, or to anything in our world. Their timescale would be completely alien to us. A microbe eating radiation from a rock might take 1,000 years to divide a single time. It would be a life form existing in a state that borders on geological time itself. Are they the original, or at least a very ancient form of life on Earth, hidden from the chaos of the surface? Or just an evolutionary curiosity? We simply do not know yet. But the possibility is fascinating. It suggests that when we look at the trench, we may not be looking at just one ecosystem. There could be two, stacked right on top of each other. One is the world we know, living on the leftovers from the sun. And the other is a completely separate shadow world, living on the faint, slow energy of the rock itself. So, the ecosystem of the trench is defined by these two very slow economies. There is the steady, sparse rain of marine snow, which supports a life of extreme patience. And then there is that theoretical shadow biosphere, which may be living on a timescale of thousands of years by consuming rock and radiation. Both are lives of profound scarcity. But every once in a while, something happens that breaks all the rules of this starving world, an event that delivers an unimaginable bounty, a single, massive, and completely unpredictable jackpot. It is called a whale fall. Imagine a 40-ton humpback or a 90-ton blue whale dying in the sunlit world, miles above. Its massive body, too heavy to float, begins the long final descent. It falls for days, sinking through the twilight, past the midnight zone, and into the deep abyss. When it finally hits the bottom, it is a revolutionary event for the seafloor. In a single instant, a single point on the barren, muddy plain is gifted with more nutrients than it would normally see in hundreds, or perhaps even thousands of years. It is a mountain of flesh, fat, protein, and bone suddenly arriving in a food desert. And then the feast begins. This feast happens in distinct, fascinating, and specialized stages, each with its own community. First, the mobile scavengers arrive. The call goes out through scent, and any creature that can move quickly converges. The ghostly snailfish, the supergiant amphipods, and, if the depth is right, the slow-moving, ancient sleeper sharks of the deep. They arrive in a frenzy, stripping the carcass of its soft tissue. This is a violent, chaotic stage that can last for many months, or even a couple of years, until the bulk of the flesh is gone. Then, when the large scavengers have moved on, the second wave arrives. These are the opportunists. The area is now fundamentally changed. The surrounding sediment is soaked with liquefied fat and nutrients from the decay. This enriched mud attracts a new community of smaller creatures, crabs, worms, and smaller crustaceans that live in the mud. They don't feed on the whale itself, but on the now rich soil and the bacteria blooming within it. This stage can last for several years. Finally, the most alien and longest stage begins. All that remains is the skeleton, but the bones are not empty. They are packed with rich fats and oils. Now, a specialized community of chemosynthetic bacteria arrives. They begin to break down these lipids, releasing sulfide, the same chemical found at the black smokers. This chemical release, in turn, feeds a new community. A strange plant-like worm called Osedax, or zombie worm, lands on the bones and bores into them, eating the fats within. Clams, mussels, and other creatures begin to grow on the skeleton itself. The whale's own bones have become a new, temporary hydrothermal vent. The skeleton has become a living, breathing reef. This final specialized ecosystem can last for 50, 70, or in some cases, even 100 years. A single whalefall is not just a meal. It is the creation of a temporary island, a complex, self-contained world. It's a way for life to create hotspots of diversity in the endless mud, and a single massive death in the light creates a new, thriving world in the dark that can last for a human lifetime. A whalefall is a natural event. It is the cycle of life and death, enriching the abyss in a way that has gone on for millennia. But the trench's most defining feature, its extreme, crushing isolation, has made it a candidate for other, less natural objects. For human history, the deep ocean has always been the perfect hiding place, and the Mariana Trench is, by definition, the deepest, most secure, and most permanent hiding place on Earth. If you wanted to drop something you never ever wanted to be seen again by human eyes, where would you put it? You would put it 7 miles down, you would drop it into the Challenger Deep. This is not just a modern idea. This dark, strategic value was recognized almost as soon as the trench's true depth was known. And that discovery happened at the precise moment humanity was entering its most paranoid and secretive era, the Cold War. This is where the verifiable facts end and the deep, unsettling speculation begins. We know that the US Navy, which funded and operated the Trieste, had an intense scientific and strategic interest in the trench. But what was the true nature of that interest? Theories have circulated for decades. The most common is that the trench was used as a graveyard. In the high-stakes game of Cold War technology, experiments failed, spy planes crashed, and sometimes rival submarines or technology were captured, or at least recovered. What do you do with a failed top-secret prototype or the wreckage of a Soviet craft that you don't want them to know you have? You can't bury it on land. It might be found. You can't just sink it in the ocean. It might be recovered. But if you tow it over the Mariana Trench and scuttle it, it is gone forever. It is an object erased from the world, protected by a lock of 16,000 pounds per square inch of pressure. And then there is the sound. We spoke earlier of the deep sound channel, the trench's bizarre ability to carry noise for thousands of kilometers. The US Navy in the 1960s knew this better than anyone. They were, at that very moment, deploying a secret, global network of hydrophones called SOSUS, a system built for one purpose: to track the movement of Soviet submarines, It is a very logical, if unconfirmed, theory that this network would have extended into or near the trench. It would be the perfect, naturally amplified listening post for the entire Western Pacific. Are there still classified, passive arrays down there, hidden in the silt, listening? We may never know. The records, if they exist, are sealed. These are not stories of monsters or phantoms, but of a very human kind of secrecy. The logic is cold and clear. The trench is a military asset as much as it is a scientific one, and it is highly likely that down in that dark mud, buried beneath the whale bones, lie other, harder, more angular secrets, the refuse of a global conflict, dropped there by the surface world in an age of fear. But those potential military secrets, those intentionally hidden objects, are perhaps only a small part of a much larger, more troubling story. The trench's isolation made it a target not just for things we wanted to hide, but for things we simply wanted to forget. For most of the 20th century, the deep ocean was treated by the industrial world as an empty space. It was a convenient, near-infinite void. The philosophy was simple and almost universally accepted: out of sight, out of mind. We believed with a kind of naive confidence that the sheer volume of the ocean would dilute our problems to nothing. We believed that what sank into the deep would, for all practical purposes, simply disappear. And so we dumped. Across the globe for decades, we used the deep oceans as a default landfill. We dropped millions of tons of industrial chemicals and heavy metals like mercury and lead. We scuttled ships filled with leftover, unwanted chemical weapons from old wars. And then there was the most difficult waste of all: radioactive material. From the 1940s through the 1980s, many nations, including the United States, saw the deep ocean as the most logical, low-cost solution for their nuclear waste. They sealed low-level and in some cases high-level radioactive slurry and contaminated materials into steel drums, often encased in concrete, and simply dropped them over the sides of ships into the deepest parts of the sea they could find. The Mariana Trench, being the deepest and most remote, was not immune. It was, in fact, a prime candidate. The logic seemed sound at the time. The idea was that the trench was geologically stable, remote, and deep enough to contain anything. The waste would be isolated from humanity forever. But this logic, we now know, was deeply flawed. Those steel drums were not designed to last for millennia. They were certainly not designed to withstand the combined assault of corrosive salt water and 16,000 pounds per square inch of pressure. The pressure can buckle them, the salt rusts them. Over decades they corrode, they implode, and they leak. And the trench, it turns out, is perhaps the worst possible place for a leak. It is not an open plain where currents can disperse and dilute the problem. Because it is a deep V-shaped trap, it concentrates what falls into it. The toxic materials, the heavy metals, the radioactive isotopes, they do not just wash away, they leak into that fine, pale sediment. From there they are absorbed by the simplest forms of life. They are taken in by the giant amoebas. They are ingested by the amphipods sifting the mud. They quietly and invisibly enter that slow, patient food web. We went looking for an alien world, a place of phantoms and strange biology. But what we are finding, buried in that pale silt, is a quiet and uncomfortably familiar echo of our own industrial age. And yet, our relationship with the trench is perhaps about to enter a new and even more complicated phase. We have used it as a dumping ground, a place to discard what we feared or what we no longer wanted. Now we are beginning to look at it as a treasure chest. The irony is that the very same features that create such unique life in the abyss, the hydrothermal vents, the black smokers, are the source of this new, intense industrial desire. When that 400-degree mineral-rich fluid from the Earth's mantle hits the cold seawater, It creates those billowing clouds. But when that smoke settles, it doesn't just form dust over thousands of years, it builds up massive solid deposits. These are called polymetallic sulfide chimneys, and they are essentially highly concentrated ore. They are packed with copper, zinc, silver, and gold. But more importantly for our modern economy, they are extraordinarily rich in rare earth elements. These are the minerals that power our 21st century lives: the cobalt in a phone's battery, the neodymium in an electric car's engine, the terbium in a laptop screen. On land, these minerals are becoming harder and more politically complicated to find. But in the deep ocean, they are just sitting there, piled high around these ancient, unstudied vents. This has triggered what many are calling a new gold rush. It is a quiet but frantic technological race to the bottom. Dozens of nations and private corporations are, at this moment, designing and building the machines to do it. We are talking about giant robotic harvesters, submersible grinders and bulldozers, each the size of a small building, that can be lowered 7 miles down and operate in total darkness. Their purpose is simple: to land on the seabed, crawl over these unique, life-filled chimneys, and grind them into slurry. This slurry would then be pumped up a massive hose miles long to a processing ship on the surface. The plan is, in effect, to begin the strip mining of the deep ocean floor. The consequences are difficult to overstate because these vents are not just rocks. As we have learned, they are the oases of the abyss. They are the only points of concentrated energy and life for hundreds of square kilometers. This kind of mining would not just disturb the ecosystem, it would annihilate it. It would be the equivalent of bulldozing an entire rainforest to get at the soil underneath. The giant tube worms, the blind crabs, the shrimp, the bacteria, the entire unique food web that lives on chemosynthesis would be instantly destroyed, and the damage would not likely be contained. The grinding process would kick up vast, choking clouds of sediment, plumes of silt that could drift for miles, burying and suffocating neighboring ecosystems that were not even the target. We are standing on the verge of being able to systematically remove an entire, unique biosphere. A world we have only just discovered, a world that might hold the secrets to the origin of life itself, all for the raw materials to build our next generation of electronics. And yet, this destructive industrial-scale gold rush is not supposed to be possible. On paper, the Mariana Trench is not some lawless frontier. It is, in fact, one of the most highly protected marine environments on the entire planet. In 2009, the vast majority of the trench and its surrounding waters were designated as a marine national monument by the United States. It is a protected sanctuary. This designation sounds powerful. It sounds absolute. It conjures images of a pristine, untouchable wilderness, a national park for the deep. It legally prohibits commercial fishing and, most importantly, resource extraction like deep-sea mining. But this protection, like the map of the trench itself, runs into a difficult reality. The first, most obvious problem is enforcement. A national park on land has rangers. It has gates. You can see the border. How do you patrol a place that is 7 miles deep and covered in permanent darkness? How do you stop a robotic deep-sea harvester from a rival nation from accidentally straying into a protected zone? The sheer logistical challenge is immense, but the more profound problem is one of jurisdiction. The ocean is not owned. While the US monument covers a vast area, the trench itself is a complex geological feature. Parts of it and the resource-rich areas surrounding it lie in what are known as international waters, or the high seas. And in those waters, a different authority rules, the International Seabed Authority, or ISA. This is the global body in charge of managing the ocean floor that belongs to everyone. And critically, the ISA is the very body that is currently writing the rules for deep-sea mining. They are the ones granting the exploration licenses that allow corporations to test their mining equipment. This creates a strange, bureaucratic and troubling paradox. A protected sanctuary that is bordered and perhaps even overlapped by a potential mining claim from a different global authority. And even if the mining happens just outside the protected border, the physics of the ocean do not respect human laws. You cannot stop the pollution, the toxic plumes from a mining operation, the clouds of sediment kicked up by the grinders. They will drift. Ocean currents will carry them. They will settle, burying the very ecosystems the monument was designed to protect. The designation of national monument is a necessary and noble gesture. It is a statement of intent from the surface world, a line drawn on a map. But in the cold, pressurized and silent reality of the abyss, it is genuinely unclear if that line can truly protect a place we can't even see. It is not surprising then that this place, so deep, so dark, and so fundamentally defended by its own physics, has captured our imagination in a way that goes beyond science or law. When a place on our own planet remains this unknown, this powerful, and this hostile to our existence, it ceases to be just a location on a map. It becomes a symbol. It becomes a mirror for our deepest, most primal anxieties. Long before the Trieste ever descended, before the black smokers were discovered, before we had any real idea of what was down there, the writer H.P. Lovecraft was searching for a concept to anchor his new mythology. He was not interested in common ghosts or simple monsters. He was interested in a far greater, more philosophical kind of fear, the fear of the cosmic, the unsettling realization that the universe is vast, ancient, and completely indifferent to humanity. In the 1920s, he wrote of ancient godlike beings called the Great Old Ones. And when it came time to imagine a prison for the most powerful of them, Cthulhu, he did not choose a distant galaxy or another dimension. He chose the deep Pacific. He invented a fictional sunken city called Rulia, a place of nightmare corpses and non-Euclidean geometry, where the dead god Cthulhu lay in his dark house, waiting and dreaming. Lovecraft had, perhaps instinctively, tapped into the power of the trench. He understood that the truest horror is not an active, malevolent evil. The truest horror is an indifference that has been here all along. The Mariana Trench is the real-world embodiment of that idea. It is a world that existed for billions of years before us and will exist for billions of years after us. It is a place that does not know we exist and would not care if it did. Our survival, our fears, our morality, our pollution, they are meaningless concepts at that depth. The pressure is not evil. It is just a law of physics. The darkness is not malevolent. It is just the absence of a sun it has never known. This is the trench's cultural power. It is the last remnant of a truly alien Earth existing right here within our own. It is the physical manifestation of the great, unsettling unknown. We can send our probes, we can draw our maps, we can even write our laws to try and protect it. But the abyss, it just waits. It dreams its own, slow, cold, and geological dreams. It is this profound ancient indifference that makes it the perfect cellar for the planet, a place where our imagination, confronting its own limits, stores its deepest fears. That feeling, that Lovecraftian sense of an alien world, is no longer just a fantasy. In a strange and fascinating twist, modern science is now looking at the Mariana Trench for almost exactly that reason. We are, as a species, collectively obsessed with a single defining question: are we alone? To answer it, we are no longer just looking at distant, Earth-like planets in other solar systems. In recent years, our hopes have focused on a new, much closer and perhaps more promising target: the icy moons in our own solar system. We are speaking of Jupiter's moon, Europa, and Saturn's moon, Enceladus. These are worlds that are, on their surface, completely hostile. They are frozen balls of ice locked in a deep freeze and bombarded by the intense radiation of their parent planets. But beneath those miles-thick ice shells, we are now almost certain there are vast, global oceans of liquid water. They are dark, they are cold, and they are kept liquid not by the distant sun, but by the gravitational pull of their giant planets. This constant tug-of-war flexes the moon's rocky cores, creating immense heat from friction. A dark, cold, liquid ocean heated from below by geothermal energy. This should sound familiar. It is the exact model of the hydrothermal vent systems we have found in our own deep ocean. If we are going to find life on Europa, if we are trying to design a probe that can survive the journey and know what to look for, we must first look to the Mariana Trench. It is our best and perhaps our only model for what extraterrestrial life might actually look like. Life on Enceladus, if it exists, will not be a photosynthesizing plant. It will be, in all likelihood, a chemosynthesizing bacteria. It will be a creature that thrives on the sulfur and methane of a hydrothermal vent, just like the tube worms and blind crabs of our own black smokers. Life on Europa will not be a complex, vertebrate fish, but if it has evolved, it will have had to solve the same identical problems our ghost snailfish solved. It will need to be a creature built of pressure. Its cells will need to be protected by those special molecules, piezolites, its body in a kind of gelatinous equilibrium with its environment. The trench has, in this strange way, become a field of applied astrobiology. We are studying its dark, cold ecosystems, not just to understand our own planet, but to prepare ourselves for the discoveries we hope to make on others. It has taught us that the sun is not an absolute requirement for life. It has taught us that extreme pressure is not a barrier. It is just a different set of rules. And it has shown us that if life can take root in a place as impossibly difficult as the Mariana Trench, then it is no longer quite as much of a stretch to imagine it taking root in the cold, pressurized darkness of a distant alien moon. But how will we explore these new worlds, both our own and those on other moons? The age of the heroic manned descent, the Trieste and the deep-sea Challenger, may already be over. These were incredible, singular moments, driven by human courage. But they were also extraordinarily risky, incredibly expensive, and, in a scientific sense, inefficient. A human being, encased in a massive steel sphere, is a fragile and complicated passenger. We are, after all, surface creatures. We are not built for the Hadal zone, and the engineering required to protect us is a monumental barrier. The future of exploration, it seems, is not human, it is robotic. But this is not the future we once imagined in the 1970s, with one large, clunky, tethered robot crawling on the seabed, connected by a thick cable to a ship above. That method is slow and limiting. The new generation of explorers is being designed to be something else. Smarter, smaller, and most importantly, free. Engineers are now developing fleets of small, autonomous, AI-driven submersibles. And many of these new designs are soft-bodied robots, their engineering inspired by the very creatures that live in the deep. The squid, the octopus, the snailfish. They are being built to be part of the environment, to move with it, not just to fight it with brute force. The idea is to stop sending one multi-million-dollar vehicle and instead release a swarm. Imagine a support ship on the surface, releasing not one, but 100 of these small, intelligent probes. They descend together, communicating with each other through simple pulses of light or sound. They do not need a pilot. They do not need a cable. This is where artificial intelligence becomes a necessity. At that depth, radio control from the surface is impossible. Water is a wall for radio signals. The robots must be able to make their own decisions. Their AI allows them to navigate, to identify targets, and to share information. One probe finds a hydrothermal vent. It calls to the others, who swarm the location, mapping it in 3D, taking chemical samples and filming its inhabitants, all without a single human command. If one probe is lost to the pressure or gets trapped, the mission does not end. The swarm learns, adapts, and continues. This is how we will finally begin to fill in the blank spaces on the map. Not with a single heroic spotlight, but with 1,000 tiny points of light, moving and thinking as one. This is how we will search for life on Europa. We will not send a single billion-dollar lander. We will likely melt a hole through the ice and release a swarm, letting it hunt for vents in the alien dark. The future of exploration, it seems, is not about conquering the abyss. It is about learning from it. It is about building machines that are as resilient, as adaptable, and as intelligent as the strange, soft-bodied life that has thrived there for millennia. We have traveled in our minds to the very bottom of the world. We have descended past the last light into a realm of immense pressure and unexpected sound. We have followed the story of the first explorers and their cracked window, and we have searched for a phantom fish. We have met the true, strange inhabitants, the ghostly snailfish, the giant amoebas, and the creatures of glass. We have seen the chemical oases of the black smokers, which may be the very cradle of life. And we have also seen the shadows of our own world, the plastic bag, the theories of military secrets, the barrels of nuclear waste, and the coming race to mine the seafloor. We are, in our modern age, a species obsessed with answers. We are uncomfortable with ambiguity. We have built a world of data, of satellites, of instant information. We strive to fill every blank space on the map, to solve every riddle, to leave no question unanswered. We tend to see the unknown as a temporary problem, a failure of our knowledge that will eventually be solved by more technology and more data. But this journey to the trench suggests something else. It teaches us that the unknown is not a failure. It is perhaps a necessity. The Mariana Trench's greatest secret may not be a creature, or a sound, or a geological marvel. Its greatest secret may be mystery itself. The trench is the last great bastion of the truly unknown on our own planet. It is the physical proof that we have not solved the puzzle. It is the humbling 7-mile-deep reminder that we are small, and that the world we live on is still, in its deepest parts, a profound, ancient, and indifferent wilderness. A world with no more secrets would be a smaller world. It would be a world without real curiosity, because curiosity is fueled by the genuine belief that we do not know all the answers. It is the engine of our science, our art, and our philosophy. It is the what-if that pulls us forward. We need the Mariana Trench to exist just as it is. We need to know that in an age of total surveillance, there is still a place that cannot be easily seen. In an age of constant noise, there is still a place that holds its own deep sounds. In an age where we feel we've mapped everything, we need to be reminded that we have barely scratched the surface. In the end, the true value of the abyss is not the minerals we can take from it, or even just the biological secrets we can learn from it. Its true value is its existence. It is the planet's final, quiet promise that there is always something deeper. There is always something more to discover. And there is always, still, a profound, beautiful, and necessary mystery waiting patiently in the dark.